Module 1, Lecture C, Setting Up Polars. By the end of this lecture, you will be able to install polars and configure a Python environment that supports both Pandas and polars. Verify polars installation by running simple DataFrame operations and inspecting results. And organize project files and notebooks to keep Pandas and polars examples clear and comparable. Configuring your environment. Creating a virtual environment. Before working with data libraries, create a virtual environment so your tools stay separate from the system. This environment has its own Python and packages, which prevents conflicts when different projects need different library versions. For example, one project can safely use an older version, while another uses the latest. Using separate environments gives you better control and confidence that updates in one project will not break others. A virtual environment is like a controlled workspace for your data projects, where you decide exactly which Python libraries are used, so different projects do not interfere with each other. This is especially important when you rely on both older and newer tools that may change at different speeds and may not always be compatible. By keeping each project in its own well-maintained environment, you can reliably recreate the same setup later or share it with others and avoid unexpected errors. Using virtual environments is crucial for reproducibility and collaboration in data work across universities, companies, and government. They let multiple users share the same system without interfering with each other's projects, such as students working on different datasets or teams separating production and experimental models. Even on a personal laptop, virtual environments keep projects organized and make it easier to share your setup with others. Over time, creating a fresh environment for each new project becomes a simple habit that keeps your work clean and manageable. Installing Pandas and polars. After setting up your Python environment, install both Pandas and polars using a package manager so you get the latest stable versions from an online repository. Having both libraries available lets you run the same data tasks in each one and directly compare their performance. This makes it easier to transition between them as you gain experience. Using the same Python version and supporting packages for both ensures that these comparisons are fair and consistent. When installing libraries like Pandas or polars, it is important to choose versions carefully and think about how they fit your environment. Using the newest versions may be fine for personal work, but in shared or collaborative settings, it can cause compatibility problems. You should decide whether you value the latest features or long-term stability and pick versions based on that choice. For instance, a research group might agree on fixed versions for consistency, while a data engineer might track the newest releases and accept frequent changes. This deliberate version selection supports a disciplined workflow and reduces future conflicts. After installing Pandas and polars, you should confirm they work properly instead of assuming the installation succeeded. Open a Python session or notebook, import the libraries, and do a simple task such as creating a small table and checking its properties. This quick test can reveal problems like missing dependencies before you start complex analyses. Treating installation as a process that includes verification helps ensure a reliable setup and reduces unpleasant surprises later. Python code installing Pandas and polars. Install both Pandas and Polars in your Colab environment. Then confirm that each library imports without any hidden errors. After verifying the imports, create very small sample tables with each library to ensure they run correctly. This quick check confirms that your setup is working and ready for further data analysis. The line that begins with an exclamation mark is a command used to install the Pandas and Polars libraries, often in environments like Google Colab. It makes sure these libraries are available so the rest of the script can perform data manipulation and analysis. The command is run in a quiet mode, which hides most of the installation messages and keeps the output clean and uncluttered. This installation step is essential for the script to work correctly. The code begins by importing the Pandas library with a shorter alias to make its functions easier to use throughout the script. It then imports the Polars library with its own concise alias for the same reason. Both Pandas and Polars are used to work with tabular data, such as data in rows and columns. Pandas is popular for its flexibility, while Polars can offer better performance for some data operations. This code prints a simple message to confirm that the Pandas and Polars libraries were imported successfully. It acts as a quick test to show that the import commands ran without errors. By displaying this message, the user immediately knows that both libraries are ready to use. We begin by creating a small Pandas data frame that stores temperature data in Fahrenheit. It has one column for city names and another for their temperatures. The data is defined in a dictionary that maps the label city to a list containing Denver and Miami, and maps the label temp F to their temperatures of 68 and 86 degrees. This simple structure lets us easily work with and analyze the temperature data using Pandas. We use Polars to build a small data frame that stores temperature data in Fahrenheit for two cities, Denver and Miami. To do this, we define the data frame from a dictionary where each key is a column name and each value is a list of data for that column. One column holds the city names and another column holds the corresponding Fahrenheit temperatures. This structure lets us organize and analyze the temperature data for both cities in a clear, tabular form. This code prints a brief summary of a Pandas data frame. It first labels the output as describing a Pandas data frame, then gets the shape to report how many rows and columns it has. It also collects the column names into a list. Together, this gives a quick overview of the data frame's structure and helps confirm that the data and column names are organized as expected. This code prints a brief summary of the Polars data frame, showing its shape and column names. The shape tells you how many rows and columns the data frame has, and the column names list the fields it contains. Together, this gives you a quick overview of the data frame structure and helps confirm that it was created correctly with the expected data. We create a new column in the Pandas data frame called temp C by converting the existing Fahrenheit temperatures to Celsius. To do this, we subtract 32 from each Fahrenheit value, multiply the result by 5, and then divide by 9. This calculation is applied to every row, so all the temperature data is transformed from Fahrenheit to Celsius in the new column. To convert temperatures from Fahrenheit to Celsius in a Polars data frame, we use the method that adds or modifies columns and apply the conversion formula to the Fahrenheit column. We subtract 32, multiply by 5, and divide by 9, then store the result in a new column called temp C. This calculation is vectorized, meaning it is automatically applied efficiently to every row in the data frame. The code finishes by confirming the converted data from both pandas and polars. It turns the pandas data frame into a list of dictionaries, where each dictionary is one row, and prints this to show the temperatures in Celsius. It then does the same for the polars data frame, using its own method to produce a list of row dictionaries. Printing both results makes it easy to verify that the two data frames were converted correctly and that their outputs match. This script shows how to install and use the pandas and polars libraries in Python with a simple example. It imports both libraries, then creates small data frames that store city names and their temperatures in Fahrenheit. The script checks the structure of each data frame by printing their shapes and column names. It then converts the temperature values from Fahrenheit to Celsius in both data frames and prints the updated results. This confirms that pandas and polars can perform the same basic data manipulation and produce similar outputs. Managing versions and dependencies. After your environment is set up, you need to manage versions and dependencies so pandas and polars continue to work well together. Each library depends on other packages that update at different times, which can cause bugs if versions are not controlled. It helps to treat your environment as a snapshot with specific versions of Python, pandas, polars, and related libraries that have been tested together. This makes your data work more reliable, easier to reproduce later, and simpler to share with collaborators who need consistent results. To manage your project environment effectively, keep track of the exact version numbers of libraries like pandas and polars, and record them in your setup notes. Choosing specific versions means you are relying on their particular behavior and performance, which is important for consistent results, such as in healthcare analytics or when working with large datasets. Documenting these choices allows others and your future self to reliably recreate the same environment and avoid surprises from automatic updates. This is especially helpful when you work on multiple projects with different needs, because it prevents one project from accidentally breaking another by upgrading a shared library. When working with pandas, polars, and their dependencies, treat updates as careful, intentional decisions rather than automatic changes. During important work, you can freeze your environment and test new versions separately before deciding to use them. If version conflicts appear, such as one library requiring a newer shared component, handle them by adjusting version requirements or using separate environments. By actively managing updates and dependencies this way, you reduce unexpected issues and keep your analyses reproducible and reliable. Python code: managing versions and dependencies. In this section, we will check the installed versions of both pandas and polars at the same time and show how to record these versions so you can recreate the same environment in the future. You will see how version information supports reproducible work by documenting exactly which tools were used. We will also illustrate a simple, manual way to capture a dependency snapshot by storing these version numbers in a small dictionary-like structure. Together, these steps give you a lightweight approach to tracking and reusing your data analysis setup. The commented line is telling you to use a package manager to install the pandas, polars, and PyArrow libraries. Installing these packages makes sure they are available in your environment so you can work with data frames and perform data manipulation. This is simply a setup step that prepares the tools needed for the rest of the script to run correctly. We begin by importing the Pandas and Polars libraries so we can use their data handling features throughout the script. And we also import the system module to access information about the Python environment. These tools let us check which versions of Pandas and Polars are installed and record the Python version in use. Together, this information creates a snapshot of the current setup, which is important for understanding and reproducing the environment in which the code runs. We create a dictionary to record key version information about our environment. We first get the Python version from the system module, keeping only the major and minor numbers. Then we read the version attributes from the Pandas and Polars libraries. This dictionary acts as a snapshot of the current setup, which helps with reproducing the same environment in the future. The code prints a header that introduces the environment snapshot and explains what follows. This header clearly labels the information about the versions of Python, Pandas, and Polars in use. By doing this, it organizes the output so the environment details are easy to read and understand. Overall, the header provides context for the setup being described. This code goes through each entry in the environment snapshot and prints the name of each component along with its version. As a result, you get a clear list of the versions of Python, Pandas, Polars, and any other track tools. This organized display makes it easy to see exactly which versions are installed. It is especially useful for documenting and sharing the details of your environment setup. This script records the installed versions of Pandas, Polars, and Python to capture a snapshot of your current environment. It stores these version numbers in a dictionary, providing a simple way to document key dependencies. When you run it, the script prints a short header followed by the versions of Python, Pandas, and Polars. Keeping this information makes it easier to recreate the same setup later, which is important for getting consistent results in data analysis and processing. Importing Polars basics. Importing Polars aliases. When you start using Polars in Python, it is helpful to choose a short, consistent alias for the library so you do not have to type the full name every time. This makes frequent function calls quicker to write and keeps your code cleaner and easier to read. A clear alias also helps you distinguish Polars operations from those of other libraries, so your code structure better reflects your analytical thinking. Using a clear, consistent alias for Polars is especially important when you work with multiple data libraries at the same time. A concise alias makes it easy to see at a glance which parts of your code use Polars, which reduces mental effort and helps you follow your workflow. This visual clarity also makes debugging and explaining your process simpler. Over time, the repeated use of the same alias builds muscle memory, so working with Polars becomes more intuitive and efficient. Using a standard alias for Polars keeps projects organized and easier to collaborate on. When everyone refers to the library in the same way, sharing and reviewing code becomes clearer and less error-prone, especially when moving from prototypes to production. This consistency also helps you when you return to your own projects later, because the patterns are predictable. Overall, a consistent alias improves clarity and productivity in your data work. Python code, importing polars, aliases. In this lesson, you will see how to import the polars library using a short alias and compare that alias style with the common way of importing pandas. You will learn that both libraries are typically brought into your code with concise names to make them easier to use. Finally, you will confirm that the imports work correctly by creating simple data frames with each library and printing them out to check their output. A line that begins with an exclamation mark is used as a command to install the polars and pandas libraries with pip. You typically run this in a terminal or in a Jupyter Notebook cell. Its purpose is to make sure both libraries are installed and available before you run the rest of the script. In other words, it is a setup step to ensure the necessary tools are ready for use. We typically import the pandas library with the short name PD and the polars library with the short name PL. These aliases are a common convention that keep code concise and easier to read. They also make it clear which operations belong to pandas and which belong to polars. Using consistent aliases is especially helpful when both libraries appear in the same script. We begin by building a small data table with pandas using an alias that has two columns called city and sales dollars, and we fill it with data for Boston and Dallas. We then create an equivalent data table with polars, also using an alias, with the same columns and values. By setting up matching tables in both libraries, we can directly compare how pandas and polars create and work with data frames using their respective aliases. We first print a short label to make it clear that the output we are about to see comes from a pandas data frame using its common alias, PD. Then we display the actual data frame that was created earlier. This confirms what data the data frame contains and how it is structured, while also reinforcing the use of the PD alias to access pandas. We begin by printing a label to make it clear that the following output comes from a polars data frame, which helps distinguish it from results produced by other libraries. Then we display the contents of the polars data frame that was created using its alias, confirming that it is set up correctly and showing its data. This visual check lets us verify the structure and values in the data frame. Overall, this process demonstrates how using aliases and clear labels helps keep outputs from polars and pandas easy to tell apart. This line prints a message to the console to emphasize that using short aliases, such as one for pandas and another for polars, makes it easy to tell the two libraries apart in your code. Clearly distinguishing them improves readability and helps you avoid confusion when both libraries offer similar features. In practice, this simple naming choice supports clearer, more maintainable code when working with multiple data tools at once. This script shows how to use the polars library alongside pandas in the same program. It imports pandas with the alias PD and polars with the alias PL, then creates a simple data table of city names and sales using each library. When the code runs, it prints the pandas version of the table first and the polars version second. Seeing both outputs together makes it easy to compare their data structures and to recognize which library is being used based on the alias. Polars version check. After you import a library, always check which version you are using. Different versions can add features or change behavior, which affects whether examples from books or online resources work as expected. Knowing the version gives you a clear reference point for what features are available and helps you troubleshoot when results differ. It is also essential in collaborative work because sharing the exact version makes it easier for others to reproduce your results and help debug problems. Checking the version of a library is an important troubleshooting step. If you follow a tutorial and a feature seems to be missing or causes an error, compare your library version with the one used in the tutorial. An older version may not include that feature, while a newer version might mean the tutorial is outdated. Knowing this helps you decide whether to update the library, change your code, or look for more up-to-date examples that match your setup. Regularly checking and recording the versions of your libraries is essential for keeping your project stable and trustworthy over time. In long-term work, such as a semester project or recurring reports, updates or new setups can change results in unexpected ways. By documenting exactly which library versions you used, you can recreate the original environment and understand why behavior may have shifted. This practice follows professional standards and helps ensure consistent, reliable, and reproducible analysis as your projects grow. Python code, polars, version, check. First, clearly show how to check which version of polars is installed in your environment. Explain that knowing the exact version makes it easier to compare your setup with tutorials or other systems, since behavior can change between versions. Emphasize that it is good practice to record the polars version you use so you can reproduce your results in the future. This line is a pip command to install the polars library for Python, but it is currently commented out, so it does not run. You would remove the comment marker and execute it if polars is not already installed on your system. The quiet option tells pip not to display the usual detailed installation messages, making the output less verbose. We begin by importing the polars library, a powerful tool for data manipulation and analysis similar to Pandas. To keep the code concise and easy to read, we assign it a short alias, pronounced PL. This alias lets us refer to the library quickly whenever we call its functions. Using such a shorthand is a common practice that improves clarity, especially when working with the library many times in the same program. To check which version of polars you have installed, you can read its version attribute from the library. This gives you the version number as a text value. Knowing this version helps you confirm that your setup matches the requirements of specific tutorials or other compatibility needs. This line of code prints the current version of the polars library to the console. Knowing the exact version is important for compatibility with tutorials or projects that depend on a specific release. By displaying the version, you can quickly confirm that your environment meets any required version constraints. In this example, we imagine a tutorial that requires a minimum version of the polars library. We store this required version, which is 1.0.0, in a single place. Later, we can compare the version of polars installed on our system to this required version. This check lets us confirm that our polars installation meets or exceeds the tutorial's requirement, helping ensure everything works as described. The code checks whether the installed polars version meets the minimum version required for the tutorial. It compares the current version string to the required version string. If the current version is greater than or equal to the required one, it marks a variable as true. This indicates that the environment satisfies the version requirement needed to follow the tutorial. This code checks whether the installed version of Polars meets the minimum version needed for a tutorial. It compares the current version with the required one and produces a true or false result. That result is then included in a message that clearly tells the user if their Polars setup is compatible with the tutorial's requirements. We create a short note that records which version of Polars is used in the project, using the stored version value to build a simple descriptive sentence. This note states that the recorded version was used for all monthly reports. Including this information provides basic documentation that supports reproducibility and makes future reviews of the project clearer. This code prints a project note that records which version of Polars is used in the project. Keeping this note helps document the software environment. Such documentation is important for reproducibility, so future analyses or reports can be run under the same conditions. In short, it is a simple way to track the exact Polars setup used in your work. This script checks which version of the Polars library is installed and compares it to a required minimum version, here set to 1.0.0. It prints the current Polars version, then reports whether this version meets the minimum requirement. It also suggests recording the exact version used in a project note and prints an example of how to do that. This practice supports reproducibility and compatibility with tutorials or other environments. Polars in practice. After importing the Polars library, a simple way to check that it works is to create a small example dataset, such as a few online shop sales records with columns for order ID, customer name, product category, quantity, and price. When you turn this data into a Polars DataFrame and display it, you should see a clean table with labeled columns and numbered rows. Polars will automatically infer the data types for each column. Seeing this structured output without any errors confirms that Polars is installed correctly and that your environment can handle data frames as expected. To check that Polars is working correctly, run a few simple data manipulation tasks on your sales data. For example, filter the rows to keep only those with quantities above a chosen threshold or belonging to a specific category, and confirm that the resulting table is smaller and contains only the records you expect. You can also select just a few columns, such as customer name and total revenue, or create a new total revenue column by multiplying quantity and price. If these operations run smoothly and the outputs look right, you can be confident that Polars is functioning properly for your data work. To make sure Polars is interpreting your data correctly, start by checking the summary information it provides for your data frame. Look at the described output and review counts, minimums, maximums, and averages for numeric columns like quantity and price. Confirm that these values match your expectations and that numeric fields are not treated as text, while date fields are recognized as dates. By visually inspecting the data frame and verifying these statistics, you can be confident that Polars is correctly set up for more advanced data analysis. Python code. Polars in practice. In this lesson, you will create a basic Polars data frame and display it to verify that it was built correctly. You will then perform simple operations such as filtering rows, selecting specific columns, and calculating a new column from existing data. Finally, you will inspect summary statistics to confirm how Polars behaves and how it interprets and summarizes the data. The line with the pip install command is a shell command meant to install the Polars library, but because it is commented out, it does not actually run as part of the script. Its purpose is to make sure Polars is installed in the environment, so the rest of the code can use it without errors. The quiet option is included to reduce installation messages, keeping the output cleaner and easier to read. We begin by importing the Polars library, a high-performance data frame tool for Python, and give it the short name PL. This alias lets us quickly access all of Polars' features throughout the script. Using the alias makes it easier and more efficient to call Polars methods and classes during data manipulation tasks. We define a dictionary called sales data that stores basic information about orders. It includes a list of order identifiers, a list of customer names, and a list of product categories, such as books or electronics. It also holds the quantity of units sold for each order and the price in US dollars for each item. Together, these lists form a simple dataset that we can use to demonstrate how to manipulate sales information using the Polars library. We begin by turning the sales data dictionary into a Polars data frame so it becomes a structured table. Each key in the dictionary becomes a column, and each list of values becomes the rows. This structure lets us use Polars tools for efficient data manipulation and analysis. With the data frame in place, we can easily perform operations such as filtering, selecting specific fields, and creating new, calculated columns. We begin by printing a short label that says this is the original data frame. Then we display the data frame itself. Seeing it printed out lets us quickly check its structure and values. This visual confirmation helps ensure that the data frame was created correctly from the sales data dictionary before we move on to any further analysis or processing. We begin by narrowing the data frame to only the rows where the quantity is greater than 2. Using the Polars filter feature, we specify a condition on the quantity column so that only entries meeting this threshold are kept. Rows with smaller quantities are removed. This focuses our data on orders with more substantial quantities, which are often more useful for further analysis or reporting. We begin with a filtered data table that already includes only rows where the quantity is greater than 2. To this table, we add a new column called Total Revenue in US dollars. This value is calculated by multiplying the quantity by the price in US dollars for each row. We use the With Columns feature in Polars to create this new column from the existing data. The result is a data table that now shows the calculated revenue for every order that passed the original filter. In this step, we work with a data frame that already has the total revenue calculated and select only the most relevant columns. We keep the order ID, the customer name, and the total revenue in US dollars. This narrows the data to a concise view focused on customer revenue. The result is easier to use for further analysis or reporting on customer-related income. We first print a short message to explain that the next output will display the filtered data frame with revenue information. so the listener understands the context. Then, we print the data frame that includes only the selected columns: order ID, customer, and total revenue in US dollars. This confirms that our filtering and column selection worked as intended and lets us visually verify the results of our data transformations. Using the describe function on a data table produces summary statistics for all numeric columns. It reports values such as the mean, standard deviation, minimum, and maximum. These summaries help you quickly understand the distribution and range of the data. They also let you confirm that numeric values are being interpreted correctly and reveal any anomalies or unexpected results. We print the summary statistics of the data frame to quickly check how the numeric data is being interpreted and whether it seems reasonable. By looking at these statistics, we can review key measures such as the mean, median, and standard deviation for each numeric column. This helps confirm that the data behaves as expected and supports further analysis with more confidence. This script shows how to use the Polars library to work with tabular sales data in a data frame. It first builds a data frame from a dictionary of order information, including customer, product category, quantity, and price, and prints it to confirm the structure. The data is then filtered to keep only rows where the quantity is greater than 2, and a new total revenue column is created by multiplying quantity by price. The script selects key columns to highlight customer and revenue details and prints this transformed view. Finally, it calculates and displays summary statistics for the numeric columns in the original data, giving an overview of the data distribution and helping verify that the operations were applied correctly. Consistent sample data loading. CSV loading basics. When using both Pandas and Polars in the same project, it is important to load CSV files in a consistent way so your results are comparable. Even small differences in how each library reads the data, such as treating dates as strings or handling missing values differently, can lead to mismatched data. These discrepancies can distort your analysis and lead to unreliable conclusions. A careful, consistent CSV loading strategy helps ensure that your data and findings remain accurate across both tools. Treat loading CSV files as a standardized, well-documented step in your workflow instead of handling each file differently. Decide ahead of time how you will treat headers, delimiters, and missing values, and then apply those rules consistently. This is especially important when working with data from different sources, such as public health data from multiple regions, where formats can vary. A consistent approach prevents tools like Pandas and Polars from interpreting the same data in different ways, and gives you a stable baseline so you can focus on comparing their performance rather than dealing with mismatched data. Using a consistent method to load CSV files keeps your project organized and your data ingestion logic centralized. Instead of having each notebook load the same data in different ways, a unified loading approach ensures they all start from the same dataset. This is especially important when comparing tools like Pandas and Polars, because it makes the comparisons fair and reliable. Overall, this consistency makes projects easier to maintain, supports better collaboration, and helps the workflow adapt smoothly when new data sources are added. Python code, CSV loading basics. This lesson focuses on loading CSV files consistently using both pandas and polars. The goal is to apply the same options in each library so that data types and values stay aligned across tools. You will see how shared settings help avoid subtle differences in how columns are interpreted. Finally, you will create a simple, reusable loader function that works for both libraries and supports a consistent data loading workflow. The line that begins with an exclamation mark is a command that installs the Python libraries polars, pandas, and pyarrow using a package manager. These libraries provide tools for working with CSV files and data frames. Running this command is a setup step that makes sure all required libraries are available so the rest of the code can execute without missing dependency errors. We start by importing pandas and polars, two libraries for working with tabular data using data frames. Pandas is the more established option, while polars is a newer library designed for higher performance but with similar capabilities. We also import the string IO tool from the input-output module, which lets us treat a string as if it were a file. This is useful when we want to simulate reading from or writing to a file entirely in memory without creating an actual file on disk. We begin with a small example dataset stored as a text string in comma-separated values format. The first line is a header that names columns such as order ID, order date, quantity, and price in US dollars. Each following line is one record with values separated by semicolons instead of commas. The data is intentionally imperfect, including missing entries and the word unknown to mimic real-world inconsistencies. This simple but messy dataset lets us explore how different data processing libraries handle irregular or incomplete input when they load it. String IO lets us wrap CSV text so it behaves like a file, even though it only exists in memory. This means we can use the same file-based operations and libraries that normally expect a real file on disk. By doing this, we can read and process CSV data directly from a string and integrate it smoothly into our data processing workflow without creating an actual file. We set up a dictionary of options to control how CSV files are read. In it, we choose the semicolon as the separator so the reader knows how to split the data into columns. We also tell the reader to treat empty strings and the word unknown as missing values. Using these settings ensures that different libraries handle these common data quirks in a consistent way. We load data from the CSV file using a pandas function that reads from a CSV buffer, treating it like a file. Shared options are applied, such as using a semicolon as the separator and interpreting empty strings or the word unknown as missing values. We also set data types explicitly, making the order identifier a 64-bit integer and the quantity a 64-bit floating point number to keep data handling consistent. Finally, we tell pandas to parse the order date as a date, so it is stored and managed as a proper date-time value. Before reading the CSV data again with polars, you must move the buffer position back to the start. This is done by seeking to position 0 so the next read begins at the beginning of the CSV content. It is necessary because the previous read with pandas left the buffer at the end, and without resetting it, polars would not find any data to load. We load CSV data into polars by reading from a buffer that behaves like a file and specifying that the values are separated by semicolons. We define certain entries, such as empty strings and the word unknown, to be treated as missing values. We also set explicit data types so that the order identifier is stored as a 64-bit integer and the quantity as a 64-bit floating point number, which keeps the data consistent. Finally, we turn on automatic date parsing so that any date strings are recognized and stored as proper date objects. We begin by printing a short message to indicate that we are about to inspect the Pandas data frame. Then, we use a Pandas function to display the data type of each column, so we can confirm they match the types we specified when loading the CSV file. Finally, we show the first few rows of the data frame, which gives us a quick visual check that the data loaded correctly and that any missing values appear as expected. We begin by printing a blank line and a short label to clearly separate this output from anything printed earlier. Then, we display the schema of the Polars data frame, which summarizes the column names and their data types, so we can confirm the data was loaded with the correct structure. Finally, we show the first few rows of the data frame using the head method to quickly inspect the actual values. This visual check helps verify that the data has been read and interpreted correctly, including the handling of missing values and date fields. This script shows how to load the same CSV data with both Pandas and Polars in a consistent way. It uses a CSV string that includes missing values and a non-standard delimiter, then applies shared options to read it into Pandas with specified data types and parsed dates. The script then resets the data source and reads it again with Polars, matching the same options and schema. The outputs from both libraries display their data types and a preview of the rows, illustrating that they handle data types and missing values in a compatible manner. This makes it easier to switch between Pandas and Polars while preserving data integrity. Schema alignment across libraries. When using both Pandas and Polars in the same project, it is important to keep the data schema consistent across the two libraries. This includes matching column names, data types, and any special markers such as sentinel codes. If the same CSV file is interpreted differently, for example, if one library treats a date as text and the other as a true date, operations like filtering or resampling will not be comparable. Misaligned schemas can lead to misleading performance and correctness results. So treating schema alignment as a deliberate setup step helps ensure fair and accurate comparisons. To align schemas in Pandas and Polars, first decide what each column represents and choose appropriate data types, such as strings for identifiers, date-time values for timestamps, integers for quantities, floating points for prices, and true or false values for return flags. Before loading data, check the types each library infers and correct them as needed so they match your intended design. This careful setup ensures that operations like groupings and joins in both libraries work on comparable data structures and produce meaningful, consistent results. When using Pandas and Polars together, it is important to keep their schemas aligned, especially for details like missing values and categorical data. If one library treats different kinds of missing or inconclusive values as the same, while the other separates them, your results may not match. Likewise, if a column is treated as a categorical variable in one library, but as plain text in the other, grouping behavior and performance can differ. To ensure fair comparisons and reproducible analyses, Regularly check and document how each column is represented in both libraries. Python code. Schema alignment across libraries. When comparing pandas and polars, it is important to first ensure that both libraries use matching schemas so the results are fair. The same CSV file can be read with different inferred column types in each library, which can lead to misleading differences. To avoid this, you should identify and correct any mismatched types so that pandas and polars share a consistent, well-documented schema before you compare their behavior or performance. The line that starts with an exclamation mark is a command to install the libraries pandas, polars, and pyarrow. This step makes sure all the required tools are available for the script to run correctly. Including such installation commands in a script helps anyone who runs the code automatically get the right dependencies. It is a common practice to improve reliability and ease of use when sharing code. We begin by importing the Pandas library, using it to handle data manipulation and analysis, and then import the Polars library for efficient data processing. Setting up both libraries in the same environment lets us work with data using either tool. This also allows us to compare how they represent data and align their schemas when needed. We begin with a small block of CSV data defined as a multi-line string that represents a simple orders table. It has columns for order ID, order date, quantity, and unit price, where the order ID is stored as text. The date uses a date format. The quantity is an integer, and the unit price is a decimal number. Each row is one order with its details. This compact data set with mixed data types will be used to demonstrate how different data processing libraries align their schemas. We begin by defining a temporary file name for our sample orders data in CSV format. We then open this file in write mode using UTF-8 encoding so characters are handled correctly and write the CSV text into it. Creating this file gives us a consistent data source that both pandas and polars can read. With the same input file, we can fairly compare how each library automatically infers data types from the CSV content. We begin by loading the CSV file with a data analysis library, which reads the file into a table-like structure called a DataFrame. During this process, the library automatically guesses the data type of each column based on its contents. This initial loading step is important because it tells us how the library interprets the schema of the dataset. We will later use this understanding to compare and align the schema with how polars represents the same data. Here we load the CSV file using polars and let it automatically infer the data type of each column. This uses polars' default behavior with no manual settings or adjustments. Doing this gives us a quick view of how polars understands the structure of the data. It also lets us directly compare how different libraries interpret the same data set using their out-of-the-box settings. We begin by checking the data types that Pandas has inferred for each column in the data frame. This reveals the initial schema that Pandas created from the CSV file. By reviewing these inferred types, we can spot any mismatches or unexpected types. This is important when we want the data types to align with those used in another library, such as polars, so that our data processing remains consistent across tools. We start by checking the initial schema that Polars infers from the CSV file, which means looking at the data types it automatically assigns to each column in the data frame. Printing these data types lets us see how Polars has interpreted the structure of the data. This step is important because it gives us a baseline understanding of the column types before we make any manual changes or corrections. By reviewing the inferred schema first, we can more confidently adjust data types later if needed. We define a schema for a Pandas data frame to keep data types consistent and reliable. In this schema, the order identifier column is treated as a string since it is an ID and not meant for numeric calculations. The quantity column is set as a 64-bit integer, so it can store large counts efficiently. This careful type alignment is important for accurate comparisons and operations, especially when working across different libraries. This code works with a Pandas data frame and converts certain columns to specific data types. It changes the order identifier column to a string and the quantity column to a 64-bit integer using a type conversion method. Doing this makes sure these columns follow the intended schema and keeps data handling consistent when working across different libraries. We convert the order date column in the Pandas data frame into a proper date and time format so that the values are treated as real dates instead of plain text. This allows us to perform accurate date-based operations and comparisons, such as sorting or filtering by date. To do this efficiently, we rely on the Pandas function designed for converting data to date and time objects. In this step, we define a schema in Polars, so each column in the CSV is read with the correct data type. We set the order identifier as a UTF-8 text field and the order date as a proper date type instead of plain text. The quantity column is stored as a 64-bit integer for whole numbers, and the unit price is stored as a 64-bit floating point value to allow decimals. Using this explicit schema helps keep the data consistent and accurate when it is loaded. We now reload the CSV file using Polars, but this time we provide an explicit schema so the data types match our expectations. This is important for keeping data consistent when working across different libraries. By defining the schema, we tell Polars exactly how to interpret each column, such as treating the order identifier as a string and the order date as a date. This avoids automatic type guessing that could cause mismatches and ensures the data structure stays aligned with what we defined earlier. Next, we display the data types of the Pandas data frame after aligning it with the target schema. This lets us verify that each column has been converted to the correct type as intended. By checking these data types, we confirm that our schema adjustments were applied successfully and that the data frame now matches the desired structure. Next, we print the data types of the Polars data frame after aligning its schema. This confirms that the data types have been correctly adjusted to match the schema we specified. By doing so, we ensure consistency with the Pandas data frame and verify that both libraries interpret the data in the same way. This alignment is essential for making accurate comparisons and analyses across the two tools. This script shows how to make Pandas and Polars use the same data schema so they handle data consistently. It loads the same order data from a CSV file into both libraries and lets each one infer data types, which may not match. To fix this, it defines a clear target schema where identifiers are stored as strings and dates as datetime values. In Pandas, it adjusts types using conversion methods, and in Polars, it reloads the file with the schema specified. After these steps, both libraries report matching data types, ensuring uniform handling, fair comparisons, and more reliable processing across tools. Reusable test datasets. To keep your work with data libraries clear and consistent, use a small set of reusable test datasets instead of new files each time. Curate a few well-designed examples, such as a compact sales dataset, a messy customer dataset, and a time series dataset, and use them across different tools. By running common operations like joins and filtering on the same familiar data, you create a stable basis for comparison. This makes it easier to see how each library behaves, including differences in defaults or performance, without the added confusion of changing both the tools and the data. Treat your test datasets as shared project resources rather than temporary files. Store them in a dedicated, well-organized directory with clear names and short descriptions of their purpose. You might keep a small, clean dataset for quick demos, another focused on edge cases like missing values and duplicates, and a larger one for performance testing. Use these same datasets consistently in both Pandas and Polars notebooks so you can compare syntax and results directly. This consistency makes it easier to understand differences between tools because the underlying data stays familiar. Using reusable test datasets gives everyone a consistent foundation for experiments, documentation, and collaboration. When all team members work with the same data, results are easier to reproduce, and it becomes simpler to build on each other's analyses. This shared familiarity lets people focus on new concepts instead of learning new datasets each time. As new scenarios arise, such as sensor readings or survey responses, they can be added to the collection, forming a dynamic but manageable library that works well in both Pandas and Polars. In this lecture, you learn to install Polars and configure a Python environment that supports both Pandas and Polars. Verify Polars installation by running simple DataFrame operations and inspecting results. And organize project files and notebooks to keep Pandas and Polars examples clear and comparable. Thank you for your attention. See you all in the next lecture.